Hi, and welcome to page 4 of the practice final. Where have we seen these problems before? Well, in your lecture notes, of course. We're starting with an alcohol here that reacts with something to make something. So that's probably not the best place to start. Instead, we're going to use something to react with magnesium to get this Grignard. And the Grignard does a metal insertion reaction between this carbon and that bromine. So that means that our starting material is that, where we have a six-membered ring with this bromine or secondary bromide directly attached. So that helps us with the part before it. How do we go from a secondary alcohol to a secondary bromide? Well, we need to use PBr3, phosphorus tribromide. HBr doesn't work very well, doesn't work quite as well because this is a secondary carbon once again, and it would have to go through a carbocation intermediate. All right, so let's fill in the remaining things, the reagents. We need to figure out how to go from this alkene into the alcohol. There's a couple different ways of doing that. We could use simple acid catalyzed hydration, water sulfuric acid. We could also have done oxymercuration with mercury acetate, water, and THF. Demercuration with sodium borohydride. So that would be a Markovnikov addition, but since this is a symmetric molecule, it doesn't really matter which one we use. Again, we could use the anti-Markovnikov style, which uses hydroboration and followed by oxidation. Next one, we go from the alkene, cyclohexene, to the bromide. We're adding a hydrogen and a bromine, so we add a hydrogen and a bromine, or hydrobromic acid. Final part of this page is working out the situation where we add new carbon-carbon bonds. That right here is a carbon nucleophile, really powerful carbon nucleophile that has 6 carbons. So the 6 carbons here came from the Grignard, the carbon nucleophile, which means that the other half, this side here, 1, 2, 3, 4 carbons had to come from the electrophile. So we have those 4 carbons plus a bromine added on, and that makes it into an electrophile because the partial negative on the bromine creates a partial positive on the carbon. Next part, another puzzle from lecture. We start with a terminal alkyne. This is a very strong base, which pulls off this proton. And after the first step, we have the acetylide ion. We're not asked to draw that here, but it's good to see. This is a really nice carbon nucleophile. And oh, hey, look at that. We have a nice little carbon electrophile. Go-to carbon electrophile is an alkyl halide. We start at the carbon nucleophile, electron rich. We end at the carbon electrophile, electron poor. We kick these electrons onto bromine, and we're going to have another alkyne molecule, same number of carbons on that left side, and we have 3 new carbons, 1, 2, 3 new carbons that came from the electrophile. We then want to take that alkyne and we want to reduce it down to a trans alkene, and this is done in 2 steps. Lithium donates 1 electron at a time, and then ammonia, or NH3, is going to be the proton source. It actually is 2 of each. You don't necessarily have to draw that or indicate that. It's sort of implied. But yeah, that's how we do a trans partial reduction. We do a cis partial reduction with hydrogen over what's termed Lindlar's catalyst. And Lindlar's catalyst is a deactivated form of palladium. I mean, it still has palladium in it, but it's deactivated. We're still thinking about those 2 hydrogens adding to the same side at the same time. And that's a useful way of remembering the H2 as it comes in together is adding syn, whereas this happens in 2 steps. And that's why the 2 hydrogens are added trans, because trans is more stable if you had to choose. The next one here, we're going to be adding hydrochloric acid to the cisalpine, and we have a symmetric molecule, right? We have secondary carbons on both sides. We're going to just number to make sure we don't miss anyone. There's going to be a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. And whether you draw the new chlorine on carbon 4 or 5 really doesn't matter. I'm going to go ahead and draw it on carbon 5, just because. But it could be on either, because once again, it's a symmetric molecule. And that's what we got for that. And then we have an anti-Markovnikov addition of water across the alkyne. On the single step page, I showed the reaction intermediate that it goes through an enol to help you see how you eventually do get to a ketone, which I'm not going to go through here, but I should still have 1, 2, 3, 4, 5, 6, 7, 8. And since I have the alkyne on 1, 2, 3, 4, and 5, then I can put the carbonyl on either 4, or I could have put it over there on carbon 5, but we do get a ketone. In part C, we're going to be drawing a bunch of different products after a couple of simple substitution reactions, and then we're going to indicate whether it happened SN1 or SN2. And then another component of it, we're going to indicate which reaction to the left or to the right gives a faster reaction. So a bunch of different components happening here. We'll start with giving the products. This here is going to be your leaving group, and then the cyanide ion is going to be your nucleophile. We're going to be losing the bromine, and we're going to be substituting it for a CN or a nitrile group. And that's actually going to be the same product on both sides. We're going to look side to side to see what the difference is. The very first thing that you want to check is the substitution of the alkyl halide. And if it's primary, hands down, it's an SN2 reaction. You don't have to look at the solvent, you don't look at anything else. If it's primary, it cannot happen via an SN1 mechanism because you cannot have a primary carbocation. So this is SN2, it happens in one step. The rate law for an SN2 reaction depends on both, right? So the rate law depends on both the thing with the leaving group, the substrate, and the nucleophile. Whereas in an SN1 reaction, it happens one thing at a time, so the rate depends only on the thing with the leaving group. It doesn't depend on the nucleophile. And what that means, just to go back, SN2 is dependent on both of them. So we see that we have the same one here, so obviously that's not changing. The thing that is different is that we go from having 2 molar to 1 molar. So if you increase the concentration of the nucleophile, you're going to have a faster reaction, which is what happened here. This is going to be the faster reaction. Next one, we have a nice leaving group. We have a bromine nucleophile to the left. It's going to replace that chlorine for a bromine. This had to happen via an SN1 reaction because it's tertiary. We don't look at the solvent. It's just tertiary carbocation. We think SN1. So there we go. To the right, we have a fluoride nucleophile that's going to replace the chlorine. There's our product. And again, tertiary means it had to be SN1. We go through, since we knew that it was SN1, we know that our rate law is going to, or our rate is going to be affected by just the thing with the leaving group. And since the thing with the leaving group, the substrate, doesn't change, then that means that neither reaction is faster. They have the same rate. It doesn't matter that bromine is a better nucleophile than fluorine because the nucleophile is not incorporated into the rate law. Cool. Next, we have this iodine. It's a really wonderful leaving group. And we have an oxygen nucleophile. This is acetate. Maybe helpful to draw it out like this. This is acetate. And we have the same nucleophile in both cases. We're going to just first draw the product, but because it's secondary and we're starting with the chiral center, now we have to investigate a little bit more in terms of the solvent to determine whether it's SN1 or SN2, because that's going to tell us about the stereochemistry of our actual product. The main thing that we're doing, as I said, is we're looking at the solvent. Here, the solvent is acetic acid, which is protic, and that's what protic really means. Is protic means it's acidic, or acidic-ish. It has a proton to donate. And that protic solvent is going to help stabilize a carbocation. In this case, it would be that secondary carbocation if the iodide leaves. And then once that carbocation leaves, then you could have this acetate add to that carbon, and it could add to either the top or the bottom face, which means that it is racemic. Okay. And going back to just like focus on that, because it was capable of stabilizing a positive charge, that means SN1 reaction, and our product is going to be racemic. So that means we don't have to draw a wedge or a dash. We just need to indicate that the new bond is between carbon and oxygen. So again, that right there is our new bond. To the right, we have the same nucleophile, still an oxygen nucleophile, but now we're in a different solvent. This is an aprotic solvent. Doesn't do as good of a job of stabilizing a carbocation. Instead, it solvates a transition state. This is going to happen all in one step in an SN2 reaction. So the acetate is going to do a backside attack on that carbon that's connected to the iodine. So the nucleophile comes in as the leaving group leaves. We have inversion of configuration, but we still have the same major type of functional group. It's just a single enantiomer that is formed. And that's the SN1 versus SN2 stuff. Ooh, just kidding, I'm not done. I need to compare the two rates. And this one is not, you just cannot compare the two because they go by different mechanisms. So actually, it's not too bad that I didn't show it because there is no difference, or rather there is no way to tell the difference between those two rates because they go by different mechanisms. That's page 4. See you on the next one.